So in this last video we used the paper machine and its control, and more in particular the control of the quality parameters, to illustrate that some of the concepts that have been seen in this course of linear algebra find their application in control. So before showing you a little video, I will give you a few words of explanation about the paper process, and I will assume here that the paper process is based on recovered paper bales. These paper bales are brought into the pulper using a transporter belt, and there the paper is shredded into pieces, water is added, and the paper dissolves, and this produces stock. And this stock has a certain consistency. So this is an amount of fibers expressed in kilos over the whole amount of stock. This consistency is controlled. This is not shown here on the slide, and then it leaves the pulper to go through centrifugal cleaners. Okay, so the heavy parts are rejected, and this stock that has been cleaned of its heavy parts goes through several stages of screens and filters to remove the finer parts. So depending on the type of paper that you produce, there might be de-inking and bleaching. De-inking is destroying the colorants from the inked, and bleaching is brightening the pulp. Finally, this pulp is stored in the machine chest. Then the stock is pumped from the machine chest to the head box that you see over here. Okay, and the purpose of the head box is to deliver the stock through a lip, so that you have a jet that is formed over here and that falls on in the wire. So this wire is in green over here, and in yellow brown you have the paper web. So the paper web is formed because the water goes through the wire and by gravitation, and the paper web is formed. So first you use gravitation, and then you use draining, and you use here a dandy roll. This is a roll that applies pressure to the paper web and kind of absorbs water. Okay, and then further on over here you use vacuum and suction boxes to remove additional water. At the end of the wet end, the paper web goes into a press section. There the paper web is pressed in between cylinders, and in between the cylinder and the paper you have a felt, so that the water that is in the paper web is transferred to this felt. This felt is also continuously rotating, and the water is removed here by dryers that you see over here. At the end of the press section, the paper enters the scanner press, where some quality parameters can be measured, for instance grammage and moisture. After leaving the scanner at the press, the paper enters the dryer or dry section to remove the water that has not been removed by pressing. The paper runs on steam heated cylinders, and they evaporate the moisture. Usually the drying section has a hood, and in this case it's not represented, and this is used to conserve the heat and energy. You will see that in the video. The vapors are removed by fans to prevent condensation in this hood. After leaving the dry section, the paper usually goes into a second scanner, the scanner at the winder, again to measure some quality parameters, and subsequently the paper is winded on a reel at the winder section. The video that you're about to see is based on the references that you see here on the screen. The different parts described in the video, the pulper, the wire section, etc., they come from different machines. Very often also old technology is shown, for instance at the wire section, but showing old technology has the advantage that it's easier to see things and easier to explain things.
Fiber products come partly from the items in your recycling bin, but also from schools, office buildings, printing shops, and other industries. This is what we call the urban forest. Everything you put in your recycling bin ends up at the sorting plant. Paper and cardboard is compressed and tied into bundles to make them easier to transport.
The delicate paper web is now carried into the press section by continuously looped wet felts, which carry away most of the water and stop the sheet from tearing. The longer section of the paper machine contains the drying cylinders. These huge heated rollers dry the paper, giving it the strength to become self-supporting, ready for the processes which will determine its surface qualities.
The QCS or quality control system controls the paper quality. In general, that means that grammage expressed in grams per square meter and moisture expressed in percent are measured by the scanners and controlled. The average values of moisture and grammage across the paper web are controlled. This is called machine direction control. Well, moisture is either controlled using speed or steam pressure. If speed is used, you're influencing the amount of time that the paper web stays in the dry section. If you're using steam pressure, then you're directly influencing the temperature of the steam heated cylinders. Grammage is controlled using stock flow, but you have to take into account that the speed is changing because of the moisture control, okay, and speed is acting as a disturbance on the grammage. Since it is known and measured, you can use feed forward to reject it. So this is MD control. In this presentation we will focus on cross-directional control, and the slides on MD control will be skipped. Well, in this talk we'll focus on CD control, cross-direction control, cross-directional control, and we'll focus on grammage. So the idea is that you try to decrease the spread of grammage around the average value across the paper web, and you can do this by locally opening and closing the slice or lip, and this will be explained later on in the presentation. So here in this presentation we'll focus on grammage control. You can see there on top of the machine that you have the head box with all the actuators that allow you to open and close the lip locally. So normally what you have is a scanner at the end of the machine. Okay, so this is not a realistic situation. This is what is indicated by this thing over here. There is a huge distance between the head box and the scanner, but this is just to explain you. So you have here machine direction, what we call machine direction, and cross direction, and as the name indicates, cross direction is across the paper web. So what happens is that the paper is traveling at a high speeds. We'll give you figures later on, and then this scanner is traversing over the paper web, and this is the trajectory of your scanner over here. So let us look at the MD value, the machine direction value, and this is the value that is used to control grammage in machine direction. At all times, the value of the quality parameter that you control, and we'll assume it's grammage over here, is the average value over the last two scans. Okay, so this is the machine direction value. It will not be of importance in this presentation since we'll focus on cross-directional control. So for CD control, you use CD profiles, and these profiles, they are obtained from the last scan of the scanner, and the scan is going from one side of the paper web to the other side of the paper web. So for instance, the profile in orange, well, it's from the scan that you see there in orange, that was from the right side to the left side, and the profile in blue is from a scan from the left side to the right side. So profiles contain a number of measurement boxes, usually 500 to 1000, and the profiles are represented with respect to the average value of the profile. And the idea of CT control is, of course, to make sure that the spread around the average value becomes as small as possible. It is assumed here that the speed of the scanner is sufficiently fast when compared with the dynamics, so that you don't have any machine direction effects on the cross-directional CD profiles. So here are some figures for paper and board machines. In cross direction, the width can go from 3 meters up to 10 meters. When you look in machine direction, the distance from headbox to winder, if you take into account that you go through the press section and the dry section, so you take the actual paper length, well, then this distance can vary from 200 meters up to 500 meters. The number of actuators that you can use for cross-directional control varies from 30 to 120. So this is, for instance, the case for grammage control, where you have a certain number of actuators so that you can influence the lip opening and locally influence the grammage. And so the speeds of these machines goes from 60 meters per minute for board machines. These are slow machines because the grammage is high, and the speed can go up to 1500 meters per minute for fast machines with the low grammage, for instance for newspaper machines. So as I've said, I've skipped the section about MD control, and I will focus on CD control, cross direction control. Machine direction control is about maintaining the profile average on set point. Of course, MD control, well, it's kind of a prerequisite for CD control, so you should give it certain attention. Cross direction control is about minimizing the control profile spread, the variation around the profile average. There are different types of cross direction control for grammage, moisture, and for instance polyethylene coating. We'll focus here on grammage, and we'll focus on solutions where you control the slice or lip opening, as you will see. So in the next two slides I explain CD control. If you put all actuators that are controlling the lip opening at 50%, you're bound to have profiles that look like the ones that you see over here, and the orange profile and the blue profile. There is a certain spread around the average value of grammage. This is simply because, well, it's impossible to control the flows of stock precisely on the wire, so that you would have something that is uniform across the paper web. Okay, so you can see that there are low frequency variations on these profiles, and it's these low frequency variations that you would like to remove by acting on the lip opening actuators and by influencing the lip opening locally. You hope to, well, increase or decrease the grammage at certain spots. Well, if you have a good CD controller that is acting, you should end up with profiles that look like the ones that you see on the screen. You can see that the low frequency content has been removed and that you're left with the high frequency content. This is normal because, well, just because of the structure of the paper and because of the fact that the distance between the actuators does not allow you to do an infinitely fine CD control. You can see that the CD controller has adapted the lip openings locally so that you have a uniform spread of grammage across the paper web. Okay, so we'll talk a little bit more about CD control, and we'll see that it is quite a challenge to implement it, and that it will use some of the topics that we have seen in this linear algebra course. I have skipped a few slides on filtering, machine direction filtering and cross-directional filtering. They have little to do with linear algebra, so have skipped them. It's something that you can see by yourself, and the slides are there for your information. A far more interesting problem is the problem of mapping. You might have seen that in our profile we have a number of measurement boxes that does not match the number of actuators. Let's say we have 500 measurement boxes, and in our case we have 13 actuators. So how are we going to control our actuators? Using what information? So we see here that we would like to aggregate our information that we have in our profile to obtain something that can be usable to control grammage and to, well, actuate on the lip opening. So in summary, we would like to go from a profile that is in measurement boxes, okay, and that has a lot of resolution, to a lower resolution profile where you have on the x-axis the actuators, okay, so that you obtain a grammage measurement for each of the actuators. This is called mapping. Well, it turns out that mapping is not that easy. Mapping, remember, is, well, assigning a given measurement box in your profile to a given actuator box. So as you have seen in the video, there is cutoff directly at the head box, but there is also sometimes cutoff at the winder. In order to do your mapping, you'll have to know how much has been cut off at the head box and at the winder. Another challenge is shrinkage. When the paper is drying, it's shrinking. It's the same as your t-shirt. When you're washing it and you're drying it, it's shrinking also. But what makes it worse is that sometimes the shrinkage is not linear. Okay, so the shrinkage is not the same across the width of the paper. There are zones that are shrinking more than other zones. You have to take into account that the actuator zones and the actuator width are not the same everywhere. Another problem is that the paper is wandering around in cross direction. Okay, this is detected by the scanners. They use photocells to turn and they measure the position of the paper web. But this means then that the mapping has to be redone on a scan-to-scan basis. Well, the edges of the web are usually not seen by the scanner. What you do very often is that you let your scanner go as close as possible to the paper edge and then you make it turn. You want to prevent your scanner to go over the paper edge, because then, well, the voltages inside your scanner head, they take complete different values, okay? And then when your scanner comes back on the paper web, it takes some time before your measurement becomes valid again, and you run the risk of having, well, not very good values in your profile. So here you see things visualized. Remember the cutoff, and this is something that you have seen in the video about the paper process, and here you have the shrinkage. So this means that, for instance, the width of the paper over here is different to the width of the paper over here. Remember also that the paper was wandering from one side to the other, okay? And the mission is now, when you have here a measurement box, okay, measurement box X, to which actuator are you going to assign it? So this is an example of mapping. It's linear mapping in this case, but first of all I want to tell you that this is not for a paper process. In a paper process the average shrinkage is around 3 or 4%, and you can see over here that the shrinkage is around 40%. So this corresponds to a process that is called polyethylene coating. You can see that indeed every measurement box has been assigned to an actuator, and this has been done linearly, and this results in a constant shrinkage. Well, in some cases you're not satisfied with a constant shrinkage or a linear mapping. For instance, you would like the shrinkage to be larger at the edges, which is often the case for this type of process of polyethylene coating, but it is also in the case in the paper process. For instance, the paper is drying better at the edges, so there is always a little bit more shrinkage at the sides, okay? So you have to devise an algorithm that allows you to have shrinkage that is varying. So this one works here by setting the average shrinkage and then by playing with the shrinkage in the middle. So if you decrease the shrinkage in the middle, as you have set the average shrinkage, it will be, well, the shrinkage will go up at the sides, and this leads to a non-linear mapping, but you still have a way to assign a measurement box to an actuator. So in some cases you want to set the shrinkage constant in the middle and, well, varying at the sides. So this leads to a mapping that is linear in the middle and non-linear on the sides. So here you can set the width of this linear zone and then set the average shrinkage, and then by decreasing this value over here, you increase and decrease the shrinkage at the sides. So let us take the example of mapping with a linear zone. In this particular case, at some stage, I cannot go too much in the details, a number of measurement boxes here has to be mapped on a distance over here, and it has to be done using a so-called neck-in function, and it will be a fourth order polynomial. Fourth order polynomial because, well, fourth order polynomial means 5 parameters to set, and there are 5 conditions. So this leaves us with a curve fitting problem where you have 5 equations and 5 unknowns. Okay, well, you have to implement this on a PLC, a programmable logic controller. So this is where the course on linear algebra comes in. You're going to implement that using the most efficient algorithm, and this is the algorithm that we've seen, Gauss elimination with back substitution. Well, the next challenging problem is coupling, and it will involve, well, quite a lot of linear algebra. So we assume here that all the actuators are at 50%, and to make things easy, well, that the profile that is measured at the scanner is completely flat. So we can ask the question, what would happen if we open the actuator that you see there in blue at 60%? So as you expect, the grammage is going up at the spot that corresponds to the increase of the actuator, and the increase of the actuator has caused a bigger lip opening and a grammage that is higher. But what you see also, and this is due to the nature of the lip that is in bending, that a little bit further away the grammage is going down, and even further it's slightly going up again, and then you, well, kind of lose the influence of this given actuator. So when you move one actuator, you have influenced the profile over a whole zone, but in particular zones you go up and in other zones you go down. Well, if you combine coupling and mapping, you have of course the measurement based profile that we have already seen, but then you obtain also an actuator based profile in which, well, each actuator gets a measurement. Okay, and you see that indeed the measurement that has been assigned to the blue actuator has increased, but you see also that the measurements assigned to the actuators that are right next to the blue actuator, they have decreased. So this is the phenomenon of coupling. The blue actuator is not only influencing its own measurement, but it's also influencing the measurements that have been assigned to other actuators. So if you don't take this into account in your control, this is going to give rise to problems. So here you see the whole picture, coupling with mapping. So you start from a measurement box profile that is mapped to an actuator box profile, and every actuator gets a corresponding measurement. We have seen that one actuator is influencing several measurements. Okay, another way to see this is that one measurement, and you see here the one in darker blue, is influenced by several actuators. This is the coupling phenomenon. Well, if you want to take the coupling effect into account, you will have to quantify it and construct what is called a coupling matrix. So you put every actuator on a fixed value. Here it is 50%, and here in this case there are 16 actuators, and then you wait until you have steady state. And well, since all actuators are at 50%, you expect a flat mapped profile. Okay, for the sake of the argument here, all mapped boxes are at 100 grams per square meter. Of course, in reality there will be some variation, and you'll have to take that into account. Then you can change the position of one actuator. Here, for instance, actuator 11 is brought to a position of 60%. Then you have to wait until all dynamic effects have disappeared and that you're in a steady state, and you'll have a corresponding mapped profile. This is the profile that you see on the screen. Then you can take the difference between this steady state mapped profile and the one that you had when all actuators were at 50%. Well, you can store the information that you collect from this test on actuator 11 in the coupling matrix that you see over here, and the interpretation is as follows. So if I increase the opening of actuator 11 by 10%, I see an increase of 10 grams per square meter in the corresponding mapped box 11. So this gives me a gain of 1 gram per square meter per percentage increase. So this is what you see over here. Okay, you see also that actuator 11 has an influence on the neighboring mapped boxes 10 and 12, and there you see a decrease of 5 gram per square meter. So this leads to these gains here, minus 0.5. Okay, so this is this coupling effect. Actuator 11 has an influence also on neighboring mapped boxes. And then you see that actuator 11 also leads to an increase of 2 grams per square meter in the mapped boxes 9 and 13, and this leads to these gains here, 0.2 over here. You see that actuator 11 does not have any other influence on other mapped boxes, so this explains the zeros that you see over here. So here we have done tests on actuator 11, but of course you should do the testing on all actuators, and if you do this you can fill your coupling matrix and obtain in this case a matrix that is 16 by 16. Here for simplicity we have made the assumption that the coupling effect is the same for each actuator, but it could very well be that the coupling effects are always different. Okay, so that you have here, for instance, other values than you have over here. What you can see is that this matrix here, this coupling matrix, will be what is called band diagonal. So you will see that I have skipped quite a few slides. This presentation here focuses on the overall CD control, so how you can construct the control structure, but also how you can implement that on a PLC so that you can test your controller up front before you actually test it on the actual system. So for that you also need a model of the system. Okay, this is all explained. If you have a model of the system, then you can start testing things on your PLC on this model, and for instance, see what happens if you have chosen the wrong mapping, if you have chosen the wrong decoupling. Okay, this is, well, a course on linear algebra, so I will focus here on the aspects of decoupling, because here they are an illustration of the course. These slides are there for your information, so feel free to have a look and to ask questions if necessary. The cross-direction control problem is a multivariable problem. Okay, remember that you have a number of actuators, that is n act, okay, and that you have a corresponding number of measurements that is given in this mapped profile. Okay, so these are grammage measurements, and you have n act measurements, one corresponding to every actuator. As usual in control, well, you need also a set point. Okay, so here is this set point. Of course, it is also a set point profile, so you need a set point for every actuator. Okay, so we can stack that in vectors, and this is the grammage set point vector, this is the grammage process value vector. Okay, and in the end what we expect over here are actuator positions, and they can be stacked also in a vector, and they should be produced here by a PI algorithm, a proportional integral controller. If you take the difference between your grammage set point and your grammage process value, this leads to an error vector, and this error vector, well, you cannot feed it directly to the controller because this is the well, coupled error. And if you feed that directly to the controller, this will lead to problems because the PI controllers will start fighting one another. So what you have to do is construct what is called the decoupled error, and that you can then feed directly to your PI controller. In this vector here we have errors where you have removed the coupling effect, so you can make the assumption then this decoupled error can be brought to 0 by only acting on the corresponding actuator. So the decoupled error vector is constructed from the coupled error vector by computing c minus 1 times the coupled error vector, and this is equivalent to solving this equation over here. So when you have constructed your decoupled error vector, you can do as if there are n-act single input single output problems. You have decoupled the problem, and in here you have, well, n-act PI controllers in parallel. Well, to do the decoupling, you will have to compute the inverse of the coupling matrix. So here is a small summary of the Gauss-Jordan elimination. So you take your matrix, you put an identity matrix next to it, and then you start, well, creating zeros below and above the pivots, and in the end, well, you obtain a system where on the left you have an identity matrix and on the right you have the inverse of the matrix. This is a small reminder of this Gauss-Jordan elimination. So the approach that has been followed is to compute the inverse of the coupling matrix. You will see that it is maybe not the best approach and that you can do better if you know a little bit about linear algebra. But anyway, you need to compute the inverse of a large matrix on a PLC. So what you'll do is use Gauss-Jordan reduction. Luckily, you need to implement it just once, and so you can compute this matrix just once and then store it. Also, it's not time critical because you can compute this matrix up front, for instance when the machine is not running or when your CD controller is in manual mode. So you'll have to implement this in a smart way, so you'll have to decompose your Gauss-Jordan reduction and the computation of your inverse over several cycles, and you'll put this in OB1. This has nothing to do with Obi-Wan Kenobi from Star Wars, but OB1 is the organization block for cycling program processing. This means that the cycles are not always the same. You do not expect numerical problems because this matrix is diagonally dominant. Okay, so generally there are no problems when you compute this inverse. And a comment that has to be made: the coupling matrix is band diagonal, so you have lots of zeros, but in general the inverse will be a full matrix. So the inverse of the coupling matrix has to be computed just once, but the decoupled error has to be computed each scan using this equation over here. So you have a problem of multiplying a large matrix with a vector here, which is the coupled error vector. Okay, when you proceed as such, well, you do not take the sparseness of the problem into account. The sparseness is take into account the fact that you have lots of zeros in your coupling matrix. Okay, but by computing c minus 1 here, the inverse of the coupling matrix, you have a full matrix, and there are not a lot of zeros in this inverse coupling matrix. So when you compute this product over here, well, you'll have lots of operations, and in general the number of operations will be proportional to the square of the number of actuators. Well, a better approach consists of using the LU decomposition of the coupling matrix, and here is a small reminder of the LU decomposition. So you start by creating zeros below the pivots, and then you obtain a upper triangular matrix. That's the matrix U, and the matrix L is simply obtained by taking an identity matrix and then plugging in the multipliers that you've got over here. So this multiplier here, you find it over here, and it has been used to create a 0 over here, so you just put it over here, and this is your L matrix. So here is your coupling matrix, and remember that this is a sparse matrix with lots of zeros, and usually the coupling width, this parameter over here, CW, is not very high. So remember that if we had done a test with actuator 11, we had seen something on the profile that was like this. Okay, so what we define as the coupling width is the influence on neighboring measurements. Okay, and here this coupling width is equal to 2. In general, the coupling width, well, is small with respect to the number of actuators. So what you can do then is take the LU decomposition of this coupling matrix. It will be, well, quite quick because this coupling matrix has lots of zeros, and you'll end up with two matrices that are band diagonal. Okay, so you'll, for L, you'll have ones on the diagonal, and then you'll have here a number of non-zero elements on the subdiagonals, and well, the number of these subdiagonals is exactly equal to CW, the coupling width, and you'll have something similar for U over here. So remember that we are solving the problem CED is equal to EC. This is what you have got over here. So this is the decoupled error vector. That's the one you're looking for. Okay, this is your coupling matrix, so you know it, and this is your coupled error. So this is a system of equations where the matrix C is always the same, okay, and it's always the, well, this vector that is changing. This is a system of equation. AX is equal to B, where the B is changing all the time. And we had said if you have that type of problem, then it's useful to decompose A in LU. Well, this is exactly what we'll do. We'll decompose C in LU, and this is C over here, sorry. And then you can write two systems of equation, one like this and one like this. Okay, you can see that if you plug in this one in here, you have indeed LU times ED is equal to EC. The advantage of these two systems of equations is that here you have a lower triangular matrix, and here you have an upper triangular matrix. So here you'll be able to use forward substitution, and here you'll be able to use backward substitution. So it will be very quick. So what you have to do is to do this LU decomposition. Okay, as for the inverse of the coupling matrix, you need to do this only once. It's not time critical, and you can, well, implement this in a smart way in OP1 over several cycles. Okay, this computation will actually be easier than to compute the inverse of the matrix C. You can see that by taking these two systems of equations, okay, and using this lower triangular matrix L and upper triangular matrix U, you take the sparseness of the problem into account, because in L here you have lots of zero. So when you're doing forward and backward substitution in these two systems, there will be lots of operations that will be easy because of these zeros in the matrices. And if you take if you look at the number of operations that you will have to do, well, it's proportional to an act times the coupling width. Remember that with the previous solution we had something that was proportional to an act squared. Okay, so the number of operations is seriously reduced because, well, the coupling width is usually much smaller than the number of actuators. So here I guess things are maybe a little bit clearer. So this is Ly is equal to EC, okay, and then once you have computed y, you can solve UED is equal to y. This is the one you're looking for. So this is the first system that you solve over here, and for free you have already a system that is in a form that is easy to compute. L is lower triangular. Okay, so what you'll do is forward substitution. Okay, well, y1 is easy to obtain. You just read it from the matrix and then you can start doing this forward substitution, and things will be even easier because you have here lots of zero. You take the sparseness of the problem into account. When you have computed your y, you have this second system of equation, and again you have something that is easy because u is upper triangular, and again you'll have lots of zeros. Okay, so you take the sparseness into account, and here you'll use this backward substitution. So you see that a lot of the things that we've seen here in this course on linear algebra find their way into practice. Here it's in a control problem on a paper machine, and remember that we had to solve a system of equations to do the mapping. We had to compute the inverse of a matrix for this decoupling problem, and we could have been a little bit smarter by doing things more efficiently using the LU decomposition.